The questions are not spoken aloud during the test, only comments on the answers. Read a question through and work out your answer. Use the datasheet on page 225 of the textbook when necessary. Then press play to check your answer and listen to the comments. You'll need to turn autoplay off to get the best effect. Keep a check of your score as you go along. There are 19 questions and 80 marks to be scored. The amount of energy needed to heat m kilograms of a substance through a change in temperature of delta theta degrees is given by the expression shown here, where C is the specific heat capacity of the substance. The mass of the water is found by using the fact that mass is equal to volume multiplied by density. Remembering that 1 degree Celsius has the same magnitude as 1 Kelvin, we can substitute into the energy equation to get this expression. And the energy required works out to be 472,500 joules. Using energy E is equal to power P multiplied by time T, we can rearrange this to give an expression for the time taken. Substituting and calculating shows that the time taken to heat this amount of water is 157.5 seconds, which is about 3 minutes, and after all there will be some heat loss to the surroundings. Of the 4 options available, C is the best. First, we write down the equation relating the average kinetic energy of gas molecules to temperature. Now, all the molecules in air are at the same temperature, so they will have the same average kinetic energy. This means that the more massive oxygen molecules must have a slower average speed, and this one statement eliminates all of options A, B and C, so the answer is D. The ideal gas equation states that PV equals nKT, so PV over T is constant. This means that a graph of pressure against the reciprocal of volume would be a straight line. That's Boyle's law. So both graphs A and B are wrong. Graph C means that PV and not PV over T is constant, which is also wrong. So the answer is D. The key to many questions involving units is that the Newton, N, is a name for kilogram meters per second squared. This is because force is mass multiplied by acceleration. In the datasheet, G has the units newtons meters squared per kilogram squared. Substituting units in the expression G multiplied by ME, we get this relationship. And substituting again for newtons gives us another relationship that we can simplify to get the answer meters cubed per second squared. So the answer is A. (210) and 206 are the nucleon numbers for polonium and lead respectively. This means that the decay has caused the nucleon number to be reduced by 4, and so an alpha particle must have been emitted to balance the nuclear equation shown here. So the answer is A. The nucleon number of the beta- particle is 0, so the nuclear equation for bromine 85 decaying into a krypton atom is as shown here. So the answer is C. start by writing down the equation for simple harmonic motion. Where a is the acceleration we require, f is the frequency of oscillation, and x is the displacement of the mass from its freely hanging position. We can calculate the period t of the motion to be 1.41 seconds, and from this the frequency to be 0.709 Hz. Now the maximum acceleration will be when the mass is at its maximum displacement of 50 millimeters, or 0.05 meters. Substituting in the simple harmonic motion equation, we get this expression. And from this we can calculate the maximum acceleration to be 0.99 meters per second squared, which is about 1/10 of the acceleration due to gravity. So the answer is C. The maximum acceleration will be when the mass is at its maximum displacement. This happens at both the top and the bottom of the range of the oscillation. So the answer is D. Radiation flux is measured in watts per square metre. It measures the power per unit area through a surface. You may remember that the Sun produces a radiation flux of more than 1,000 watts per square metre at the Earth's surface. Only option B has a phrase implying per unit area in it, and it also has the power. So the answer is B. Beware of reading quickly through the 4 options offered. They are all designed to look possible. Always look at the question first and try to answer it. This could involve quite a bit of calculator punching, but it's easy to get lost with all the pluses, times and minuses. A neat way to solve the problem is to realise that it is the extra 0.0073 atomic mass units of the proton and the extra 0.0087 atomic mass units of the neutron that make up the difference. So the total mass deficit of the carbon-12 atom is just 6 multiplied by the sum of 0.0073 and 0.0087 atomic mass units. And this gives 0.0960 atomic mass units. The answer is B. From the kinetic theory, we deduce that temperature in Kelvin is proportional to the average kinetic energy of the molecules in a substance. So a temperature of 36 degrees Celsius is not twice as hot as a temperature of 18 degrees Celsius. We must compare the Kelvin temperatures. Remember that a Celsius temperature has to have 273 added to it to get the equivalent Kelvin temperature. We can now calculate the ratio of the Kelvin temperatures by dividing one by the other. The ratio works out to be 1.062, which is about 0.06 or 6% bigger than 1. So we could say that the temperature is about 6% hotter in Hong Kong, and it is the physicist who is correct. The answer to part A is that an ideal gas is one that obeys the equation of state PV equals nKT under all conditions of temperature and pressure. In part B, you need to say that a real gas behaves like an ideal gas so long as the pressure is not too large, and that the gas is above a certain temperature called its critical temperature. In part C, we rearrange the ideal gas equation so that we can calculate N, the number of molecules required. and then substitute the data in the question into this equation, along with any data required from the datasheet. You must also remember to convert to the Kelvin temperature and to write the volume in cubic meters, which would get you a mark even if you subsequently made an arithmetical error in your calculation. And it works out to be 6.01 times 10 to the 23 molecules, which is about 6 times 10 to the 23 molecules as required. Though it is not asked for, this is definitely a case where a sketch will help in solving the problem. The process of drawing the sketch will help you to understand the situation. The annual movement in the question refers to the difference in the positions of the star as seen from Earth against the very different background stars at an interval of 6 months, say from the beginning of January to the beginning of July. The light from the star a distance d away approaches the Earth at slightly different angles, θ1 and θ2. Note that in questions like this, the angles are so small that sin theta is about the same as tan theta, which is about the same as theta radians. Try it on your calculator. The difference between the angles θ1 and θ2 is 0.017 arc seconds. That is 0.017 divided by 3,600 degrees. And that works out to be 4.7 times 10 to the minus 6 degrees. So the distance E1, E2 is 3.6 times 10 to the 18 metres multiplied by tan of 4.7 times 10 to the minus 6. And that works out to be 2.95 times 10 to the 11 metres. You need to keep your wits about you as you get towards the end of a question like this. This distance we have worked out corresponds to the diameter E1, E2 of the Earth's orbit round the Sun. So the radius of the Earth's orbit is 1.5 times 10 to the 11 metres to 2 significant figures. In Part A, your diagram should look like the one shown on screen. The y-axis shows how much bigger or smaller the luminosity L of a star is compared with the luminosity of the Sun, L0. The x-axis shows the Kelvin temperature of the stars. Both scales are logarithmic. The temperature scale has high temperatures to the left and low temperatures to the right, but this was not asked for here, and it will emerge from your answer to Part B. In Part B, this is just the earlier diagram completed by showing the position of the Sun as shown here. Red giant stars are cooler than the Sun, and their position to the right of the Sun on the x-axis confirms your knowledge of the back-to-front nature of the temperature axis. In Part A, a supernova is an exploding star whose luminosity rises by a huge factor in a matter of days. The bracketed part of the answer is probably not needed to get the mark. Supernovas can be used as standard candles because it is believed that their maximum luminosity or brightness is always the same. In Part B, red shifts are all about identifying absorption lines of known elements in the spectra of distant galaxies and seeing how far they are moved towards the red end of the spectrum. The required recession velocity can be calculated by identifying a particular wavelength lambda in the spectrum from the galaxy and measuring the difference in wavelength delta lambda compared to the same line in a laboratory spectrum. This is the red shift. This is hard work for just 1 mark. The Doppler effect formula then allows the recession velocity to be calculated, and it works out to be 9.0 times 10 to the 6 meters per second. In Part C, the first method involves measuring the maximum radiation flux F from the supernova at the Earth's surface. You then use the inverse square law, F equals L max over 4 pi d squared, to calculate a value for d, the distance from Earth to the galaxy. The value of L max is known and is the same for all these supernova explosions. The second method makes use of Hubble's law to give a second value for d using the recession velocity calculated in Part B. Note that these two values may not be the same. Part C more or less tells you what to consider in your answer, but if you haven't thought of this before, it's not easy to spot the two processes. It was only in the last few years of the 20th century that astrophysicists compared these two values for distant galaxies. In Part D, gravitational attraction between all galaxies would be expected to be slowing down the rate of expansion. In Part A, to explain how the uranium was U-235 rich 2 billion years ago, you need to get an idea of what the percentage of U-235 in uranium ores was then. So we can calculate what the proportion N of U-235 was back then as shown on the screen. And it works out to be 5.6%. So the uranium was U-235 rich. Part B is a suggest question. This means that you are not expected to know the answer, but to have a go. When the proportion of U-235 was high, there would have been fission occurring, provided that the groundwater acted as a moderator to slow down the neutrons. As the reactor worked, this water would have evaporated, eventually closing down the reactor, until more water gradually seeped in. In Part C, scientists could test the chemical composition of the reactor core and find the elements that U-235 is known to decay into. Part D is a how science works question about the environment. The fact that this natural fission reactor has remained in one place for over 2 billion years suggests, contrary to popular opinion, that we can perhaps safely bury the radioactive waste produced by modern nuclear power plants. The long-lived radioactive products of this natural fission reactor in Gambia have not leached away into the surrounding groundwater. This is a question that does not lead you through a series of calculations step by step. As such, it is the sort of question that might form part of a stretch and challenge task, or test the synoptic component of an examination. For Part A, you will need to calculate the laboratory wavelength of the hydrogen absorption line, then the observed red and blue shifts of this line, and then use the Doppler formula. The average wavelength is half the sum of the two wavelengths given, and it works out to be 656.282 nanometers. The Doppler shifts for star S as it moves directly away from and directly towards star M are calculated by working out the differences between the two wavelengths given in the question and this average wavelength. Moving away from m, this works out to be plus 0.041 nanometers. The Doppler formula can be rearranged to give an expression for v, the orbital speed of star S. Substituting and calculating shows that the orbital speed of S is 18,750 meters per second relative to star M, and this is about 20 kilometers per second as required. In part B, now that we have values for its period t and its orbital speed v, we can calculate the orbital radius of star S by rearranging the expression for evaluating circular velocity. Substituting and calculating shows that the radius of the orbit of star S around star M is 8.1 times 10 to the 11 meters. To tackle the second part of B, you need to use Newton's law of gravitation and apply your knowledge of centripetal acceleration. Star S is moving in a circle under the gravitational pull of star M, so we can use Newton's second law as shown here. ms and mm are the masses of stars S and M respectively, v is the orbital speed of S, and r is its orbital radius. This rearranges to give this expression for the mass of star M. Substituting and calculating shows that the mass of star M is more than 10 to the 30 kilograms. In Part A, alpha particles cause terrible internal cell damage because they are strongly ionizing. Because of this, they are absorbed by a thin layer of tissue and so are difficult to detect outside the body. In Part B, you need to realise that 1 year is not an exact multiple of 138 days, so we will need to use the radioactive decay formula shown here. We must first find the value of the decay constant lambda, which is given by this expression. Substituting and calculating shows that the decay constant is 5.02 times 10 to the minus 3 per day. Now we rearrange the radioactive decay formula and substitute our data to work out that the amount of the sample remaining after 1 year is 16%. Note that we can make the calculation easier by keeping the decay constant in days to the minus 1, and then using a time of 365 days. It is not necessary to convert both to seconds. If you are good at maths, you could do the calculation even more quickly using the method shown here. In the last bit of B1, 3 years is nearly 8 half-lives, so your curve should decay to almost 0, but not quite. Even though this is a sketch graph, you should show that after 1 year the activity has fallen to 0.16 of its original value, as you have just calculated. In part 2 of B, we have already worked out that the decay constant is 5.02 times 10 to the minus 3 per day. We can calculate the activity of 1 microgram using the equation shown here. We need to convert the decay constant into seconds to the minus 1 when substituting the required values. Substituting and calculating shows that the activity of 1 microgram of the isotope is 1.7 times 10 to the 8 becquerels. In the first part of C, to calculate the power generated by 1 gram, we need to multiply the activity we have just calculated by 1,000,000, and then by the energy of each alpha particle, remembering to convert the energy into joules. It works out to be 144 watts, which is about 140 watts as required. In the last bit of Part C, if 1 gram of the polonium-210 generates 140 watts, that's equivalent to a couple of filament lamps, and it was sealed in a small glass capsule, then the glass would heat up rapidly and would almost certainly melt. In Part A, your diagram should include only the forces acting on the student. As she goes through the midpoint, she experiences no acceleration, and so the resultant force on her must be 0. There are just 2 forces acting on her, the pull of the earth vertically downwards, her weight, and the push of the seat on her bottom vertically upwards, the normal contact force. These 2 forces are equal and opposite. At the end of the first oscillation, she will experience an acceleration back towards the centre of her motion, which is provided by the horizontal component of the push of the seat. There are still just 2 forces acting on her. The 2 diagrams shown here are all that is needed to get full marks, but it is worthwhile considering the second case in a bit more detail. Let's resolve the normal contact force into vertical and horizontal components. The vertical component, r cos theta, is equal and opposite to the weight, mg, leaving a resultant force of r sin theta acting towards the centre of the motion. In the first part of Part B, the most likely reasons for the motion not being simple harmonic are that the swing is initially making oscillations with a fairly large angle, and that the motion is quite heavily damped. In Part B too, you need to realise that the graph shows displacement plotted against time, and so the velocity is the gradient of the graph at any particular point. Therefore, you need to draw a tangent to the curve at the point where the line cuts the x-axis for the first time. Using a large triangle, you can determine the gradient as shown here, and it works out to be 2.5 meters per second, and this is the velocity required. In Part C, before we use the SHM equation, we need to calculate the frequency f of the swinging motion. That's how many oscillations there are in 1 second. Now we can substitute into the equation for simple harmonic motion. Remembering that the maximum value a sine function can have is 1, this simplifies to V max equals minus 2 pi multiplied by the frequency and the amplitude. Substituting our values, we get, and the maximum velocity works out to be 2.5 meters per second. Note that this value may differ somewhat from the value you calculated from the graph. This is because the graph is drawn to a small scale, giving rise to inaccuracies in determining the gradient. In Part D, to demonstrate resonance, a student could give the seat a firm push every time it reached the end of its swing. The frequency of the applied driving force would therefore be the same as the natural frequency of oscillation of the swing. Energy will then transfer from the person pushing to the swing, and so oscillations of large amplitude will build up. Note this is an explain question, not a describe question. So the first 2 statements are essential because they explain why resonance occurs.